So moving on, I mean, we have a lot of questions about like how do we actually fairly compare this to models. So luckily, we are going to hear about small-scale modeling. First from Azadeh.
All right, thank you. Thanks, Yao-Yuan organizers for inviting me. I'm another one of the party crashers. I haven't been here in the 3 years ago in the previous one. So I'm well, with Coral and Ethan, we're going to talk about the basically, well, you can see it about the modeling the low mass and abundances, quenched fractions, and stellar mass halo mass relation. I think we're not going to touch a lot on quenched fraction. It's mainly on the stellar mass, halo mass, and abundances. I will mainly kind of give some sort of an overview from the simulations on the kind of classical dwarf regime. It would be a magnitude of -8 or brighter, or stellar masses of about 10 to the 5. Coral will touch upon lower mass ones, and Ethan will talk about the kind of the observations and the empirical models we have. I think I don't need to motivate a lot that why we kind of care about these low mass end. That is where the halo mass function is quite steep, but the stellar mass function doesn't seem to be very steep. And I guess it looks like basically universe is relatively empty-ish when we look at the dwarf regime, but there are lots of subhalos or smaller dark matter clumps that we want to know how to map these into each other. And I'm not going to kind of expand a lot on abundance matching. We heard a lot about it yesterday, about basically how abundance matching works and what it predicts. I just want to kind of highlight how these relations look like on the low mass end. This is from Peter's recent work kind of comparing different abundance matching and other empirical relations. I guess they are not exactly abundance matching these days, but the relations that we have, and I did some precision cosmology with PowerPoint, and you see how things look like on the low mass end. Basically, at 10 to the 9, if these different models can predict basically 3 orders of magnitude in stellar mass. So I think I just want to kind of give a reminder that we should not use these abundance matching relations at the low mass end. They are not designed to, or they have not also been tested at these low mass, and they have very large uncertainties. On top of that, in the discussions, it came up like a couple of minutes ago, that how this, even if the principles of abundance matching with it, which is this monotonic relation between stellar mass and halo mass, even works. So where we are with kind of cosmological simulations predicting this relation at the low mass end, I will talk about a few different simulations, just a quick, very quick recap of what these are. You're going to see a lot of apostle because simply I worked on them. These are typically zoom-in simulations of either Milky Way or local group, in this case, local group. This apostle is based on the Eagle galaxy formation model. And basically, we run them at resolution of about 10 to the 4, and we look at the predictions. The other simulations you're going to see in some of my plots are they're from different teams with different models. Just you're going to see Auriga, which are Milky Way simulations with a galaxy formation model similar to TMG, but not exactly, actually, especially at the low mass end, there are differences. You're going to see some from Fire Group, Latta and Elvis, and Nihal. The only thing I guess you need to remember if you don't know these simulations is that these are typically again either Milky Way or local group-like environments, and they have been run at similar-ish resolution, about 10 to the 4 or so in baryons. So what these models predict for us, this is particularly the stellar mass, halo mass for field galaxies, not satellites. I will talk about satellites if I have time towards the end. That's how things look like in a puzzle. These are simply two different colors or two different resolution. The lower resolution is kind of yellowish and the higher one is red. I just wanted to highlight that because the Eagle hasn't been calibrated on the highest. Basically, we're pushing the simulations to a regime that hasn't been tested, that potentially could be dangerous, but actually it gives us a pretty good convergence, at least for stellar mass, halo mass. And these simulations predict the right number of satellites for Milky Way or dwarf galaxies around the local group as the stellar mass function you see on the left. I'm just going to flip through a few other models. You're looking at results, again, field galaxies, not satellites, from Elvis or Latte, from Shay's work, Garrison and Kimmel 2019, I think. And you can see this, they get also the right stellar mass function for the Milky Way satellites, and M31. This is the panel on the left. And surprisingly, well, surprising to me when I made the plot like last week, they actually work, they look quite similar to what we had in Apostle, at least in terms of the slope of the relation. The other model that I compared with is Eureka. Maybe you can see by eye, there's a bit of offset, especially at these regimes. They're a bit higher and looks to be a bit more scattered, but they also produce the right stellar mass function for Milky Way and the one from Miha group. These are also follow kind of similar trend. And finally, just for comparison, a few individual dwarf galaxies from Coral's work and Monshi. These are high resolution of individual dwarf galaxies, not a volume like Loco group or Milky Way. So I think the message is basically, despite all the differences that these models have, actually they predict the right number of satellites down to 10 to the 5. There is a large halo to halo scatter though, as you can see, maybe in the case of Auriga, it's quite similar, quite clear. The halos span a very small range, well, 1 to 2 times 10 to the 12. But you can see the number of satellites would be different. Also at the kind of lower mass end, all of these relations are quite steep. At basically all, except for maybe some of the Auriga ones, I don't know what exactly is going on, but basically all these models predict that if you have a stellar mass below 10 to the 7, the halo mass is around 10 to the 9 to 10 to the 10. So these are kind of what these models, again, despite all the differences, predict. Going a bit to kind of thinking and pausing about what this relation means, just here as an example for one of these cases, that is basically the steep shape at the low mass end. Actually, again, it came up in the previous discussion, raises the question that whether even these principles of abundance matching works, or in another word, basically the scatter in the y direction is very large, that I'm not sure we can even do abundance matching or any kind of relation we assume if reality looks like something like that. If you know the halo mass of an object, let's say halo mass is, I don't know, 3 times 10 to the 9, can we know the stellar mass of the object? At least these models predict that at a fixed halo mass between 10 to the 9 to 10 to the 10, the scatter in the stellar mass could be easily 2 orders of magnitude. The other thing that I guess worth mentioning is some halo occupation that in some of our works we call dark fraction. I just want to make a note that we should be very careful about interpreting. We at least, hopefully we've been clear that these usually mean halos above a given stellar mass, because this is the resolution of the simulations. For example, in this case of Apostle, this is halos with a stellar mass more than 5 times 10 to the 4. What it means, does it mean they are actually dark or not? I think it's a tricky question, and I think it's not very clear whether they're actually dark or they host very tiny low mass dwarf galaxies. But I think the conservative interpretation is that basically the scatter in the y direction is large, between 10 to the 9 and 10 to the 10. You can have a galaxy that is 10 to the 7 in stars or below 10 to the 4, again, almost 2 or 3 orders of magnitude. So what sets the stellar mass at a given halo mass? There is a really nice work from Alex Fitz and Mike Boyle and Colchin that they are taking, these are from the FIRE simulations, they're taking some of these halos that have almost at the final time, they have very, very similar halo mass, about 10 to the 10, but when you spread them in Vmax, basically the stellar mass, which is the color coding here, correlates with Vmax, so maybe Vmax is actually more telling us about what it means. To put things in context, I plotted this on the same panel, just Vmax instead of halo mass. You're going to memorize this plot by the end of my talk. You can see that actually the relation is still very, 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 very steep. Even though there seems to be a relation between Vmax and stellar mass, it's not clear. Again, if we know the halo mass or Vmax, we can know what the stellar mass could be. I have like 1 minute. I just quickly go over the satellites. The picture is more complicated when we want to talk about satellites because they also lose mass. Here on the left, you're going to see the field dwarfs, and on the right, satellites of Milky Way and M31, color-coded by how much mass they've lost since infall. So basically, they all move to the left, and also they don't move much vertically because they lose a lot of dark matter before they lose the stars. So basically, all of them move to the left, and as they lose more mass, they move more and more to the left. We should compare this with observations. That also adds another complication. This is the same stellar mass, halo mass, Vmax, for fields and satellites. But for observations, I'm going to be done in 30 seconds. Thanks, Yao. For observations, we don't observe Vmax. We observe the circular velocity at a given radius. In this case, for dispersion-supported systems, like most of the dwarf we see in the local group, this is the half, we can measure the circular velocity or enclosed mass at the half-light radius. That's how they look like on this plane. I just want to say that they can tell us about what the scatter and maybe slope of the stellar mass, halo mass should be, at least, because as I said, tidal stripping moves things to the left on this panel, and also V1/2 is always less than Vmax. So any relation here, just for guide the eye, I plotted Mostra and Beruzzi 2013. Any stellar mass, halo mass should basically live on the right hand of these measurements. Basically, if your stellar mass, halo mass in the field follows something like Beruzzi, we cannot explain the galaxies that are basically having this high velocity. I'm just going to end here, kind of mention my conclusion or the questions that we should still understand. What is the slope and scatter of the stellar mass, halo mass relation at the faint end? And even when we know the slope and scatter, what determines the stellar mass at a fixed halo mass? And I stop here and give this to Coral.
Thank you.
Great. Thanks. Yeah. So I think it's a sort of a sign of how far we've come that Ozzy didn't really talk about everyone's favorite problem, missing satellites problem. And go ahead and advance to my two favorite quotes about it. That's probably because a lot of people are getting tired of hearing about this. Carlos Frank threatening to leave the room, and more recently, Andrew Wechsler kind of banging his hand on his fist. He probably didn't do that, but in my mind he did, claiming there is no missing satellites problem. Go ahead and advance the slide. And that's because down to about a stellar mass of 10 to the 5, which is what Ozzy was really talking about, above the ultra faint regime, you can go ahead and just put everything up on the screen here. There really is no missing satellites problem. It's really only in the ultra faint regime below about 10 to the 5 that the regime of ultra faint dwarfs that we may or may not have a missing satellites problem. And just to kind of show you what you're seeing, this is from a review of both Bullock, Boyle, and Quenched et al. We have the observations in purple, pretty much matching up with extrapolations from abundance matching in gray. But depending on what the faint end slope is, yeah, we might have a problem at the low mass end, we might not. So this is sort of left an unanswered question. And if we, okay, go ahead and advance. And if we then, as simulators or as theorists, want to see if there is this problem, or if we want to have this problem or not have this problem, we need to answer some questions, or at least ask some questions with our simulations. How many galaxies of a given mass do we predict around the Milky Way? And can we observe these galaxies? Go ahead, Ethan, and throw up the questions. Related to the first question is my favorite. What's the lowest dark matter halo that can form a galaxy? We still don't know this. And then you might see a lot of people talking about, as you mentioned, the dark fraction. What fraction of halos are dark at a given mass? And then I'm going to spend a little time talking about whether we can observe these galaxies. What's their effective surface brightness? Go ahead. So to kind of try to get these two questions, I find the following two plots super helpful. Of course, stellar mass, halo mass relationship, where you can see a selection of extrapolations of abundance matching. Again, as I mentioned, and as many people mentioned, these are somewhat meaningless in this mass regime. but you know, somewhat useful, I guess, to make sure we're not way off, or to at least learn from. And then on the right, the mass size relation, where you have half-light or half-mass radius on the left and stellar mass on the x-axis, and some observations, classical Milky Way dwarfs as open circles in the DES year 1 and year 2 results. So I'm going to sort of use these two slides. Okay, so to get a sense of the challenges of modeling these ultrafaints, and I'm talking now about yes, the points. Just going to throw some simulations up here and show their mass resolution scale, so star particle mass, and sort of spatial scale, whether it's force softening, I think in most cases it is. And this is Illustris TNG, the highest resolution. Now this isn't super fair. Illustris isn't designed to model ultrafaints, but it does give you a sense of sort of where we stand in terms of resolution. Go ahead and put the next one up. This is Apostle. Again, Apostle is Milky Way mass, and you know, can say some things about some lower mass galaxies, but not really intended to get into the ultrafaint regime. And even Latte has about the same mass resolution. And then even Fire 1 simulations, and I'll pick on myself here, even though we had parsec level spatial resolution, I did talk about ultrafaints, and even my ultrafaint galaxies were only resolved at maybe tens of star particles. And so yeah, these are sort of the challenges that we're dealing with when we model the low mass end, especially if we want to talk about size. So in the last few years, go ahead and switch the slide. There have been many really excellent works trying to sort of get at either the dwarf or maybe the ultrafaint regime. Not in any case. There's a lot of really good papers up here with a variety. I've ordered them in baryonic mass resolution from low to high at the bottom. You can also see their spatial resolution. There's a whole range of different codes, different spatial resolutions, different density requirements. You can see in the details density requirements for forming stars, different definitions, yeah, basically different feedback prescriptions. And I don't have time to sort of get into all of it. I recommend looking at all these papers, and these aren't all the papers that are out there, it's just sort of a selection. And you can also see they each have different strengths, right? So where some might be higher resolution, you know, maybe they were only able to run 3 of them. And of course, I'm referring to myself. But the thing I want to focus on now, in particular, are the 2 columns on the right. Other challenges that maybe people who don't model this regime and don't push these sort of simulations to the limits of what they're able to achieve resolution-wise thought of, like, what do we define as a galaxy? Is it a single star particle? Is it 100 star particles? Is it a minimum stellar mass? Is it somewhere in between? And what is then the definition of the extent of your galaxy? Do you find it with a brightness profile, a surface brightness profile? Is it just some fraction of the virial radius? Do you do it by visual inspection? And I just want to chat a little bit about these challenges. Go forward. Slide. Okay, yeah, so here is the stellar mass halo mass relation. Go ahead and put everything up there. Okay, so this is you can see from some of the, I think this is from some of the simulations that I mentioned before, where they lag on the stellar mass halo mass relation. And the Egerts et al., the EDGE galaxies have 2 different resolutions, which you can see in color. They really modeled this really a cool work where they took one single ultrafaint, a 10 to the 9 halo, and then just changed a bunch of things, the feedback prescription, they added radiative transfer or not, etc., different resolutions. It's fairly interesting, but that's why they all lie in a line. Okay, go ahead and start putting up just some observations about this. Yeah, fire is systematically low by a couple orders of magnitude compared to, say, Ravaz and Jablonka. Could be resolution. I'm looking forward to the next version of that paper. They actually didn't handle ultrafaints in that paper. Anything that you can see, it kind of cuts off at 10 to the 5. Could be resolution, but go ahead and advance one more. But if you look, when Egerts et al. Takes their supernova energy and multiplies it by 10 or 100, they start to get down into our regime. So I suspect it has something more to do with the strength of feedback. Of course, feedback is handled differently in all of these simulations, but the strength of fire feedback, which causes them to be such low mass. Okay, go ahead. We see a flattening. You can see a flattening in Ravaz and Jablonka. You can see a flattening in the stellar mass halo mass relation. And really quickly, I'll mention, I see no minimum mass for galaxy formation. Every time we increase resolution, it drops lower. But let's talk a little bit about the flattening. This was also seen in Farah's work, which you can throw up. I didn't put this on the same plot because it didn't, yeah, it was, I just want to show this figure. So Farah looked at two different star forming prescriptions, one based on metal cooling, one based on the fraction of molecular hydrogen. Also really interesting paper to tell the differences between these two runs. But I'm putting it up right here now just to kind of show this flattening. And this was also seen in Sawal et al. Long ago. So I've long said I think this is a resolution issue, but it's also a galaxy definition issue. So let's go ahead and just scroll through the next few. Well, before you scroll here, this is my simulations where I've just dropped the particle. This is anything with a star particle or more. And really quickly, I want to point out we're forming galaxies in dark matter halos as low as apparently 10 to the 5. I'm not saying I believe that, but it just shows you that, yeah, there's no minimum halo formation, halo mass for galaxy formation yet. And a lot of it depends on what you define as a galaxy. But let's see what happens if we define our galaxy as 1, 3, 5. Go ahead. Yeah, perfect. So you can see this flattening. If you whether you have a stellar mass cut because the particles are about the same, a star particle count, you're going to get this sort of resolution artificial flattening. And your minimum mass for halo and for galaxy formation will also change depending on what your galaxy is. So just kind of wanted to highlight, you know, that sort of issue is something that we have to maybe not agree on, but at least be clear about in our papers when we're modeling this very low mass end. Okay, next slide. All right, in my last minute or so, let's talk about mass size. Go ahead and let's put everything up. Yeah, so, right. So most of the simulations that are not fire, or certainly the fire that are high mass, lie in the observable range. I don't know that it's a fair comparison. I mean, our stellar mass is so low, we don't really overlap in stellar mass with any of those other simulations. One of my predictions from my most recent paper was that these very puffy stealth galaxies with very low effective surface brightnesses. And just for reference, the solid line is 30 magnitudes per square arc second. The dashed line is 32.5. That's about where we hope LSST can get to. The triangles are satellites, so they may have been stripped by their dwarfs, or that just might be some sort of contamination issue. But the point is, my simulations predict these really puffy things that we can't see, then they should be everywhere. I'd be interested to see when others push down to the stellar mass that I'm getting, if they see something similar. Go ahead and put the last, yeah, so it makes sense to me why there aren't any observations up near the super low surface brightness points. We're just now, you know, we heard a lot of great work by Dragonfly at higher stellar mass, but at similar sort of surface brightnesses we're finding more and more puffy, faint objects, and I don't think that, I don't imagine that would change in the low mass regime. But why don't we make any of these compact DES dwarfs? So this got me thinking about how we define a galaxy. Go ahead and advance the next slide. What if there's an effective surface brightness cut? What if we can't see sort of the low surface brightness outskirts of galaxies? So what I did is the last couple slides, I'm just gonna take my simulations and define Rmax not by visual inspection, not by point something RVR, but by where the effective surface brightness drops below 32.3, which is Antlia 2's surface brightness. That's the lowest surface brightness galaxy we've detected yet. So let's go ahead and just flash through. Okay, so here, yeah, great. So you can see, is there a slide above this? Oh yeah, okay, so this is where with my normal definition, and then go ahead, yeah, go again, and this is where they move if you do the surface brightness cut, and they're getting at least closer to observations, suggesting, and what this hints at is that maybe we're missing sort of a low surface brightness stellar halo around these DES dwarf galaxies. And then just to give a sense of what it looks like when I put everything with 5-star particles or less, this is just a 0.2 RVR definition of Rmax, what we get with R half. And then go ahead and show where they move to. So we're not really overlapped with observations yet, but they're moving closer. And just I hope these last slides just made the point where what you define your galaxy to be and what you define your edge to be really determine your answers. And I'll let Ethan go on about more observation stuff.
Okay, great. Thanks, Coral. So Hi, everyone. I'm Ethan Nadler. I'm a grad student at Stanford, where I work with Risa. I'm going to talk about some attempts to model the faint end empirically, and in particular, I'm going to try to connect some of the dots we've heard about from the hydrosim perspective with empirical models. But I thought I would be remiss not to start with the observational progress in the last, I guess, 3 years since this conference in 2017. And there's been quite a bit. It's really quite an exciting field. So I want to make 2 points. The first one, this plot on the left, is showing all known galaxies, at least prior to this local volume satellites paper, as a function of distance from us. And there's clearly, a very significant just locus of galaxy detectability, right? There's really an observational selection effect such that we can only detect the very faintest galaxies within the virial radius of the Milky Way, and that continues to be true. So this extremely faint end, we are kind of faced with the problem of having to understand the Milky Way, I guess, whether we like it or not. On the other hand, I want to highlight the fact that there's really exciting progress going on, kind of pushing the census of faint dwarf galaxies maybe down to an absolute magnitude of -9 with the very nice local volume satellite work that we heard about from Scott. And also in the context of the SAGA survey, pushing down to maybe an absolute magnitude of -12 and building a large statistical sample in that regime that we can compare to. So I think this is rapidly advancing, and the comparison of models in kind of all 3 of these regimes is a really interesting area for work in, I guess, the next 3 years. So just quickly, I want to highlight some of the advances for the Milky Way satellite population in particular, because actually quite a bit has happened. So many of the points that I'm showing on this plot, many of these discovered satellites wouldn't have shown up on this map in 2017. In particular, there have been efforts using the dark energy camera, and they've consistently been discovering satellites sort of on the other side of the Large Magellanic Cloud from DES. For example, Maglites has discovered some galaxies. There's this Hydrus-1 system that's kind of in between the Magellanic Clouds. Antlia 2, which I'll talk about a little bit more, was discovered, or at least initially identified, using our Lyrae clustering in Gaia. And then there are these green points, which are hypersupreme cam satellites, which are particularly intriguing because what they point to is the fact that our current census of satellites is still highly incomplete at the faint end. So in particular, these deep photometric searches, such as by HSC, really continue to discover really low surface brightness dwarfs that are kind of just below the current boundary of galaxy detectability. So from a purely empirical point of view, what this tells us is that this population of known satellites is highly incomplete. And as I said, there are very complementary searches going on based on, for example, our Lyrae kind of clustering and identification and phase-based methods using Gaia. And Antlia 2 is a very nice example of this, and it's a very intriguing system in many regards because of its very large size. So that's kind of the observational stage. And I just want to talk a little bit about the attempts to model the ultra-faint end empirically. And I think there's a really important kind of complementarity that goes on between empirical models and hydro models. As we heard about from Coral, it's extremely difficult computationally to push hydrosims down to these ultra-faint scales. And so having some kind of analytic or at least empirical understanding of these relations in the ultra-faint end is quite important. So I'm going to talk, in the context of this model that we've developed in Risa's group over the last few years. But I want to highlight that there's really, cool work going on that's quite complementary. So in particular, this StatGen model, the Zheng et al. Paper that just came out is really nice, and I highly recommend you look at it. So throughout, I'm going to talk, as I said, in the context of this model that we've built, but I'm going to try to compare explicitly to other hydrosims and other models where possible. So as Ozzy highlighted, there's, if we think about abundance matching at the ultra-faint end, it's sort of uncertain in many ways. We know the field luminosity function may be down to an absolute magnitude of -13 with some, sizable uncertainty from surveys like Gamma. And then if we want to extrapolate a relation, say, between V peak of a dark matter halo and absolute magnitude of the galaxy that lives inside of it, there are uncertainties in building that abundance matching relation, including the faint end slope of the satellite luminosity function, the scatter in this relation, the onset or lack of an onset of kind of a cutoff in galaxy occupation. And the other point I really want to highlight on this slide is that the modeling of satellite size from an empirical perspective is extremely important because what we've learned in these satellite searches, for example, using DES, is that satellite detectability is really most strongly a function of surface brightness. So it's really not enough to just predict or reproduce the luminosity function. You have to kind of self-consistently model the size, distance, and luminosity distribution of satellites in order to claim consistency. And so I'm going to touch on this a little more, but there are ways to kind of extrapolate size models, the galaxy halo size models, from the kind of brighter galaxy, larger galaxy end into the ultra-faint regime that are quite interesting. Okay, so we've kind of built this modeling framework that takes, that populates essentially dark matter only zoom-in simulations using this empirical model, and then we've done quite a bit of comparison work using the kind of satellite detectability functions derived from DES and Pan-STARRS photometric searches to kind of self-consistently predict the population of observed satellites. And I really highly recommend that modelers look at this selection function paper, the Drilke, Lange, and Bechtel paper that I linked before, because what it provides is essentially satellite detectability probability as a function of satellite luminosity, size, and distance, which I think is a really key step in the comparison of these models to observations. So there are a few interesting findings from this work. One takeaway is that in order to model the Milky Way satellite population, the existence of a large Magellanic Cloud system of satellites is really crucial in order to fit the data, and in particular to fit the kind of overdensity of satellites in the DES footprint that is observed. We find evidence that basically there's kind of continuous galaxy occupation down to what we call this minimum halo mass scale. In other words, the faintest observed satellite galaxies must occupy dark matter halos with masses below, peak virial masses below 3 × 10⁸ solar masses. So I'm going to talk about some of these results a little more and then compare them to other models. So this is a posterior distribution from our FIT. I don't want to walk through all the details here, but I just want to highlight a couple big picture takeaways. So the faint end slope of the Milky Way satellite luminosity function is actually consistent with that the field luminosity function from gamma. And I think, of course, these other kind of observational efforts we heard about, including local volume satellites and SAGA, will really help kind of break degeneracies and help us nail this down better. As I said, observed satellites must occupy halos with peak mass below 3 × 10⁸ solar masses at 95% confidence. And then this size model, I think, is a really interesting point. So we actually, in the ultra-faint regime, we actually have a measurement of the amplitude, scatter, and power law index of this galaxy halo size model. And there's some interesting points of comparison as far as the concentration dependence of that size virial radius relation and so on. But broadly, it seems that our posterior is consistent with Andre's galaxy halo size model. So there have been really several efforts along these lines, basically empirical modeling efforts. So I listed some of the papers here for reference, and basically they all predict that the total population of Milky Way satellites, they're roughly 200 with some large error bar, down to maybe an absolute magnitude of 0. And all these models, generally find pretty consistent results, which is encouraging. Of course, most of these will be discovered, as was mentioned, by the Rubin Observatory. And I think an interesting point is that this faint end luminosity function slope, as was shown in this really nice paper, Munchi et al. Basically the star formation and feedback prescriptions that you assume in hydro simulations can really influence, right, the kind of luminosity of galaxies at these very faint scales and therefore their abundance. So I hope that these measurements that we're making can actually start to differentiate between such models. Okay, so this galaxy occupation fraction was touched on a bit. I just want to drive home the fact that the observational definition of galaxy is different than what's usually made in hydro simulations, at least if galaxies are defined in terms of star particles in simulations. So I think it's just really important to keep in mind that the galaxy occupation fraction is like inherently definition and resolution dependent. And so, you should just take care when reading different papers and comparing results. So the stellar mass halo mass relation, was talked about quite a bit by Ozzy. I kind of compiled some results from the literature with the help of Coral and put them on some of these plots. I should say, I would read the x-axis on these plots with a really generous error bar because our mass definitions kind of differ between these papers. But what I'm mainly looking at is the slope, and I think in terms of that, the stellar mass halo mass relation is fairly, that might be a little generous, but fairly consistent among these different simulations and our kind of empirical constraints. And I think there's really interesting work going on using other abundance matching proxies, for example, star formation rate. So there's this very nice paper by Reed and Urkel. And finally, I just want to end on sizes because I think it is quite important, and I'm glad Coral really highlighted that. So I think an interesting question, is what sets the scatter in satellite size at fixed halo mass, for example? And in particular, why do hydro simulations seem to predict ultrafeints that are generally much larger than observed? Of course, I think we heard part of this answer from Coral, in the sense that depending on how size is measured in these simulations, the points can actually move around quite a bit on actually both the X and Y axes here. So I think these are all really interesting areas for future work, and I'm happy to have a discussion about any of them. So thanks.
Thank you. Thank you, all of the speakers. Okay, so we have about 10 minutes for discussion. So there are actually very lively discussion that is taking place right now on the Google Doc. In case you haven't visited, do go ahead. I highly recommend the paragraph that Andre wrote about the missing satellite problem. But maybe for verbal discussion, we'll start with Annalisa's question about distinguishing dwarf galaxy in the field and dwarf galaxy that are satellites, and some of the discussion. That's right, Annalisa.
Yes, thanks a lot. Coral, we just needed a clarification, right? When you show your table, those are field ultrafaint dwarf in the simulations. It makes completely different to. No. Please go ahead. Yes. Yes. So
yeah, I'm just saying you're right. I meant to say that and I didn't, and that's like half the questions on the Google Doc. So yes, in order to get down to the resolutions that we're talking about for all of those, you just can't really have a Milky Way around. I spent a lot of time trying to think about how we can fix that problem, because really the only ultrafaints we see are near Milky Way, and so we're left with in all of these simulations comparing apples to oranges in some ways. I do still think it's useful, and we really have no other choice right now. But yes, none of my simulations had a massive galaxy around, and any in the table, I believe. They're all zoom-in simulations of isolated field dwarfs. Now, some are satellites of dwarfs, but that's a different story.
Thank you very much.
Alison, do you want to chime in?
Yeah, that gives me a great opportunity to actually highlight some work that my grad student is doing. Laud Applebaum is actually putting the final touches on a paper where we do actually do Milky Ways at higher resolution than have ever been published before. And we are pushing down into the ultrafaint range. And so that should be out in the next couple of weeks. So I just wanted to advertise. Stay tuned.
Yeah.
Thank you. Azadeh, do you have a question?
Yes, I'm not sure if I'm allowed to ask a question as one of the presenters. That's a question for Ethan. Something that actually, unfortunately, I didn't get the chance to point out, and I wanted you to kind of, if you have thought about it or have any comment. The fact that I think, if I remember correctly from your stellar mass, halo mass, some of these ultra faint ones are living in 10 to the 8 solar mass halos. But if we look at actually the kinematic measurements for these dwarfs, it's a large arrow bars, but most of them are actually relatively dense. They are more consistent with 10 to the 9, 10 to the 10 solar mass halos than 10 to the 8. Do you have any thoughts on that?
Yeah, so I agree. I mean, I think this is tricky from several points of view. So, I mean, I agree that the observational error bars are large. And in particular, not only the kinematic measurements, but like the extrapolation of those in order to derive a halo mass, and even to like think about self-consistently talking about that in terms of like peak halo mass as we construct it is very tricky, right? So I think that's the basic point. Like, in order to like robustly predict like dynamical mass, clearly, quite a bit more work needs to be done that accounts for these tidal effects and so on, right?
Julio.
Yes, thanks all the presenters. I had a couple of comments. I think one is the fact that I think we're mixing together very different systems when you compare satellites or tightly stripped objects with isolated objects in the stellar mass halo mass relation. halo mass can change by orders of magnitude because of tidal stripping. So when you put them all together, you get this, giant scatter, and you can't make sense of the relations. My experience with this has been, when I looked at our own simulations and others, has been that if you actually take care of only considering isolated objects, then the scatter is actually quite narrow. And if you plot, say, some characteristic mass of the halo or Vmax versus stellar mass, the scatter is actually quite small for every simulation. What happens is that every simulation predicts different relations, and you can only see relations if you actually do the hard work of eliminating the tidal stripping from that. And so I'm actually, one of the things I was alarmed when I saw Azi's presentation is that Auriga, Fire, Nihao, Apostle, they all give actually quite different stellar mass, halo mass relations on the regime that we can compare with satellites, satellite functions, for example, and numbers of satellites, but somehow, and sometimes by orders of magnitude. But then when you compare it with, say, with the satellite luminosity function or missing satellites problem or whatever you want to quote it, apparently they all fit the observations. So either we're looking at this problem incorrectly, or this satellite or the stellar mass halo mass relation is not particularly, it's such a crude, blunt measure that is not particularly helpful. So I guess I'd be interested in seeing what people comment on that, because to me it seems that we're missing something important there.
Risa, go ahead.
Yeah, I just want to say, Julio, I agree completely with the statement that one has to be very careful in comparing this relation for satellites versus field. I just want to emphasize that in our work with Ethan, in comparing to the Milky Way, those results are actually quite consistent with what you mentioned, that at peak, there is a fairly small scatter that then results in a much larger scatter at the present day. But we're actually inferring a fairly small scatter. I mean, there's still observationally uncertainties for sure, and sensitivity to the size modeling. But I think, just to say that I think the observational results of the Milky Way are quite consistent with small scatter at peak.
That's great. I guess I'd like to hear from Azi, for example, how does she respond to my comments that, how do you get the same, satellite luminosity function from systems that are, with the stellar mass, halo mass relation at peak differ by sometimes orders of magnitudes? I mean, what does it mean?
I think my gut feeling is that, does it help if I actually show one of these plots so we actually know what we're
Go ahead.
talking about? So I think that was one of the plots. Can I make this a bit bigger? So I think at, let's say at 10 to the 10, you can see there's almost an order of magnitude difference, for example, between, let's say, Apostle or Fire, which is the blue points, and Auriga. But I think at the scale, there is around something like Milky Way that we have only 1 or 2 satellites, that you can change things by 1 or 2, that things are not changing. Let's say stellar mass function is not changing. Most of the satellites are, of course, coming from this low mass end, where let's say if I remove, can I remove Auriga here? Because Auriga, it has a huge scatter, and I don't know what that is actually, to be honest. Here, for example, most of the satellites are coming from basically the slightly lower mass end, that these more or less, the slope is different, but generally, I think that if stellar mass, halo mass is relatively similar. I don't know if I responded to your...
I think what's happening is that it's a different thing. What's happening is that because the relations are similar and they're approximately power laws, then if you compute the satellite luminosity function relative to the primary, you will always get the same numbers. Right? So what's happening is that the Milky Way halo that has been assumed is changing from simulation to simulation. So provided you have things that are kind of parallel in this regime, they will all seem to have the same satellite luminosity function. I think that is what's happening. So if you actually were to compare the satellite luminosity functions of 2 galaxies, of 2 halos of the same mass from different simulations, we get the very different results. But that is not what is done. So,
yeah,
so one is, I think that's what's happening, but I mean, that can be easily checked, I guess.
I think the other problem is that the halo to halo, let's say if we were going to run exactly the same ICs with these models, I think the luminosity function won't be exactly the same. But when you want to run, I don't know, 30 halos and you have these, a factor of 3 or 4 difference in the number of satellites, at the end of the day, basically more or less all of them agree. So I think I agree with the point that maybe that is actually not the right question to ask. We get the right number of satellites with the different slope of the stellar mass, halo mass. But what are we going to learn now? I think we should maybe ask another question to understand this better.
Okay, we are one past the time. So let's thank all our speakers in this sessions again.